This is Mrs. O'Neill for AP Chemistry, Chapter 15, Section 1, Chemical Equilibrium. Go to page 640 at some point and look over those key terms. To be in equilibrium is to be in a state of balance, a tug of war in which the two sides pull with equal force. So this is Mrs. O'Neill for AP Chemistry, Chapter 15, Section 1, Chemical Equilibrium. Look over the key terms on page 640 at some point. To be in equilibrium is to be in a state of balance, a tug of war in which the two sides pull with equal force so that the rope does not move is an example of static equilibrium, one in which an object is at rest. Equilibria can also be dynamic, like when cars traveling in both directions over a bridge that serves as the entry to a city. If the rate at which cars leave the city equals the rate at which they enter, the two opposing processes are in balance. The net number of cars in the city is constant. So if we look at this picture quickly, here's our city in the background, cars going in, cars coming out. So if 5 cars are constantly going in at the same time or at the same rate that 10 cars are coming out of the city, the amount of cars in the city would remain constant. That's considered a dynamic equilibrium. So the concept of equilibrium is section 1. Should have watched that intro video, and I'm going to go through these notes rather quickly because I want to make sure there's enough time for this video. So he first talked about reversible reactions, but he talked about the reactions that you're more familiar with, reactants to products like fireworks. Fireworks explode, reactants turn into products. There's no way those products are going to go back into those fireworks. Same thing with burning wood. The wood is going to burn, turn into ashes. There's no way those ashes are going to turn back into the wood. So you already understand reactions kind of going to completion. Well, this guy talked about or saw how a reversible reaction works, where there's this special arrow that we put on these reactions because the reactants turn into products, but at some point those products can actually make reactants. And he saw a reaction between salt and calcium carbonate turning into sodium carbonate and calcium chloride, and that reaction went back and forth. Gave you that nice flow chart as always. He also did the PhET model, using balancing and adjusting the levels of reactants and products to show you how those molecules would change. He gave you another analogy about a dance and how males and females, how they're before the dance are by themselves, then they partner up, but if there's a change in song, you might want to change partners. So again, you're going back and forth. So then he did kind of the same thing or same analogy and then just labeling those males and females. So again, using that dance analogy, we have reactants going to products, but again, those products are going to change partners as they change back into reactants. So in a real reaction, and he's going to be dealing with this reaction multiple times during the course of the videos throughout this chapter, and he talks about how these two reactants are going to form into products, but back again into reactants. So a physical example, and this is one that we've already talked about, is a dynamic equilibrium when we talked about vapor pressure, right? We talked about evaporation going into liquid into a gas, but then those gas molecules are coming back down, condensating into a liquid. And especially if we have something as a closed container, we would form vapor pressure, and that equilibrium would be dynamic because the amount of water molecules going into steam or vapor molecules is going to be at the same rate those vapor or steam molecules turn back down into liquid. He talked about dissolving salt into water as a chemical example. I kind of agree and kind of don't agree with it being chemical because to me dissolving is a physical process, but again it's a good way to understand how water, and if we dissolve some salt in there, it would dissolve, you would not see it, but if we were to take the water out, somehow let it evaporate, we would see that chunk of salt reforming again. In my mind, this is dissolving and crystallizing when we talked about solubility. And then he talked about a biological example, using your nose and your senses. So I thought that was interesting, but not really need to know for the AP exam. Talked about the environmental example, again, not really need to know for the AP exam, but you actually might see a reaction or some kind of scenario about this and have to be able to explain how that carbon comes out of the soil, released into the atmosphere as respiration, and then comes back through photosynthesis. So another analogy that I have is water from a waterfall falls into a lake, then flows out to a river. Okay, so the water in the lake stays constant. It's coming from a waterfall and then going, leaving into the river. So the amount of water coming in is going to equal the rate at which that water comes out. Again, not necessarily the same amount of water. So let's say, I don't know, 5 gallons of water comes in, and I'm just making stuff up, and 10 gallons go out, kind of like I said with the cars. The amount of water, though, that's actually in the lake stays constant. Here's another metaphor. For those of you who like The Simpsons, here's our scenario. So we have 7 people on the second floor. We have 12 people on the first floor. So if we always have 2 people going up and 2 people going down, there's always going to be 2 people on that elevator at any one moment. So will the amount of people on each floor ever change? No, right? So if we started, like I said, 7 and 12, and we have 2 going up, 2 going down, the amount on each floor is always going to stay the same. If there are always 2 people on each escalator at one moment, will the specific people, though, occupying each floor change? Yes. So the different people can change, right? We always have 2 people on the escalator going up and down, so the different people can change, but again, the amount of people on the top and, the first floor and the second floor would be the same. So now let's think about chemistry and think about those reactions. So again, that double arrow tells us that this reaction can go in both directions. So reactants become products. That's going to be considered the forward reaction, while simultaneously, that's a hard word for me to say, the products react to become reactants. So we go to the forward reaction and reverse reaction. So no matter how the reaction is written, that's why we always say, always, 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 these are still going to be the reactants, even though we're talking about the reverse reaction. So reactants yields products is the forward reaction. Products yielding reactants is going to be the reverse reaction. So in a closed system where no reactants, products, energies are added to or removed from the reaction is considered a reversible reaction and also called equilibrium. So at equilibrium, the rate of the forward reaction becomes equal to the rate of the reverse reaction. And like our escalator metaphor, the 2 sides, reactants and products, will have constant amounts even though the reaction continues to occur. So they're going to constantly be going up the escalator, constantly coming back down, constantly forming products, constantly forming reactants, again, at the same rate, not necessarily the same amount. So however, like the metaphor, the equilibrium amounts, though, just like I was saying, reactants and products are usually not equal. They just remain unchanged. So in this case, again, if we're looking at the moles and those coefficients, it's 4 moles on the left and 2 moles on the right. So again, it's not going to be the same amount of reactants and products all the time. So let's see what happens here in this reaction. So we just kind of have those reactants in there. You're going to see that the forward reaction is happening as well as the reverse reaction is happening exactly the same time. I'm going to say that word that I can't, it's hard for me to say, simultaneously. So the forward reaction and the reverse reaction are happening at the same time. So this is just going to continuously happen in both directions as long as it's a closed system and the reaction already established equilibrium. So the how far does a reaction go before it actually stops? So again, you're used to a complete reaction. You're used to reactants turning into products, and it stops, right? It's done. Once it forms, or we have that limiting reactant, and once that limiting reactant is used up, it stops. However, in an equilibrium reaction, we're going back and forth. So on to your notes packet. Finally, your objective in this section is to examine or understand these reverse reactions and understand this concept of equilibrium. So pause the video, write in your blanks, and then play to hear my words. So again, it's the rate, it's the rate, it's the rate. The rate at which those products are formed equals the rate at which those reactants are formed from those products. So again, it's the rate, it's the rate, it's the rate. So we want to always keep in mind, for equilibrium to occur, neither reactants nor products can actually escape, which that should make sense. There's no way that it's going to be at equilibrium if we're going to have an open container and let those reactants turn into products. They're just going to escape into the atmosphere. So we do need a closed system in order to capture those products and allow those products to turn back into those reactants. So the rate, the rate, the rate, the rate, the rate is always going to be equal to each other. So depending on the rate of reaction, a reaction may seem to have gone to completion or not even take place at all, but it does. So reactions are reversible. Again, initially A and B have to mix in order to form the C and D, so only the forward reaction occurs, but at some point there's going to be enough C and D in order to go backwards. So then we have that reverse reaction. So if there's enough buildup of C and D, then those C and Ds are going to start making those A and Bs, and that's always going to be considered the reverse reaction. So here we have a graph, and a lot of these graphs you're going to see multiple times. So here we have the forward reaction happening, forming products. Here we have the products forming reactants, and at some point you see an equilibrium has been established. So again, the rates are equal, not the concentrations. So again, here we're looking at another graph representing concentration and time. So here we have that reaction again. So I'm going to see the process, the reaction occurring. So we have our nitrogen and our hydrogen decreasing. That should make sense, right? Because we're forming products. And we have 0 products of ammonia forming, again, increasing because it's produced. But at some point, equilibrium is established. And where is that equilibrium established? Where that concentration levels off of all 3, right? Where they're leveling off. So that's going to be our equilibrium amount concentration for nitrogen. That's going to be our equilibrium amount for hydrogen and our equilibrium amount for ammonia. So why does the graph tell you the concentration of each species? Again, those concentrations are not equal to each other. That's just their amounts at when equilibrium is established. So now let's look at rate versus time. Little different graph. So here we have again our forward reaction versus our reverse reaction. And again, where is that equilibrium established? When that rate is equal to each other. And that's how we know equilibrium is established, when the rate of the forward and the rate of the reverse are equal to each other. So here are the 2 graphs. Again, you'll be seeing multiple times. So characteristics, again, the rate of the forward equals the rate of the reverse. Always, always, always. Okay, so not in concentration as you saw in those graphs. So pause the video, read this over, see if you can answer. There's an A and a B. That should make sense. Get that into your head. Rates, rates, rates. Look that over, see if you can answer that question looking at the ratio and the equation. Hopefully you got greater than 1. And again, if you're not understanding that, that's a question you can ask me, or you will eventually, hopefully, understand how we're going to deal with those equations. All right, see you in class.